Lesson: Supervised versus unsupervised learning techniques. Supervised and unsupervised learning are pivotal branches of machine learning, each serving distinct purposes and applications within artificial intelligence. Understanding these techniques enables professionals to select appropriate models and frameworks to solve complex problems. Supervised learning is characterized by its use of labeled data to train algorithms. This means that each data point is associated with a specific output, allowing the model to learn the mapping function from inputs to outputs. Common supervised learning algorithms include linear regression, logistic regression, support vector machines, and neural networks. These techniques are particularly effective in scenarios where historical data with outcomes is available, such as predicting house prices or classifying emails as spam or not spam. In practice, supervised learning requires a well-defined dataset with clear input-output pairs. The model's performance is evaluated by its ability to predict or classify new, unseen data accurately. One practical tool for implementing supervised learning is scikit-learn, a Python library that offers a range of algorithms and utilities for model training and evaluation. For example, in a project aimed at predicting customer churn, a company could use historical customer data, including demographics, transaction history, and support interactions, to train a supervised learning model. By applying a decision tree or random forest algorithm from scikit-learn, the company can identify patterns that distinguish between customers who are likely to remain loyal and those at risk of leaving. This actionable insight allows the company to implement targeted retention strategies. On the other hand, unsupervised learning deals with data that lacks explicit labels or outcomes. The primary goal is to uncover hidden patterns, groupings, or structures within the data. Clustering and dimensionality reduction are the two main types of unsupervised learning techniques. Clustering involves grouping data points with similar characteristics, while dimensionality reduction simplifies data by reducing the number of features. K-means and hierarchical clustering are popular clustering algorithms, while principal component analysis and T-distributed stochastic neighbor embedding are widely used for dimensionality reduction. Unsupervised learning is particularly useful in exploratory data analysis, where the objective is to gain insights into the data's structure without prior knowledge of the outcomes. A practical application could be market segmentation, where a retailer seeks to understand customer behavior without specific purchase outcome labels. Using K-means clustering, the retailer could analyze customer demographics, purchase frequency, and product preferences to identify distinct customer segments. These insights can then inform personalized marketing campaigns and product recommendations. The selection between supervised and unsupervised learning depends on the nature of the problem and the availability of labeled data. In scenarios where labeled data is abundant and the goal is to predict specific outcomes, supervised learning is the preferred approach. However, when the objective is to explore data and identify underlying patterns without predefined labels, unsupervised learning is more suitable. It's crucial to note that the effectiveness of these techniques is significantly influenced by data quality and pre-processing. Clean, well-prepared data leads to more accurate models and reliable insights. Real-world challenges often require a combination of both supervised and unsupervised learning techniques. For instance, in anomaly detection, unsupervised learning can identify unusual patterns or outliers in the data, which can then be further investigated using supervised learning to classify these anomalies. This hybrid approach is particularly useful in fraud detection, where unsupervised algorithms first flag suspicious transactions, followed by supervised models that classify these transactions as fraudulent or legitimate based on historical patterns. Frameworks like TensorFlow and PyTorch provide robust platforms for developing both supervised and unsupervised learning models. TensorFlow, developed by Google, is widely used for building neural networks and deep learning models due to its flexibility and scalability. PyTorch, developed by Facebook, offers dynamic computation graphs, making it a popular choice for research and experimentation in unsupervised learning tasks. These frameworks not only facilitate model development, but also support deployment in production environments, enabling AI systems to operate at scale. Case studies further illustrate the practical applications and benefits of these learning techniques. In healthcare, supervised learning models have been employed to predict patient outcomes based on electronic health records, improving diagnostic accuracy and personalized treatment plans. In contrast, unsupervised learning has been used to analyze gene expression data, revealing new insights into disease mechanisms and potential therapeutic targets. These examples demonstrate the transformative impact of machine learning in diverse domains. Statistics underscore the growing adoption and effectiveness of machine learning techniques. According to a report by Gartner, 37% of organizations have implemented AI in some form, with supervised and unsupervised learning being the most commonly used approaches. The report highlights the importance of these techniques in driving business innovation and competitive advantage. In conclusion, mastering supervised and unsupervised learning techniques is essential for AI professionals seeking to address real-world challenges. By leveraging tools like scikit-learn, TensorFlow, and PyTorch, practitioners can implement and deploy effective machine learning models that provide actionable insights and drive decision-making. The choice between supervised and unsupervised learning depends on the problem context and data availability, but often, a combination of both approaches yields the best results. As AI continues to evolve, the ability to harness these techniques will remain a key competency for professionals aiming to excel in the field.